Hello, welcome to module number 9, Life on Jovian Moons. And this time we are going to concentrate very closely on smaller bodies that are orbiting around some of the gas giants in the outer solar system. And per our previous definitions for the requirements of life, we will be focusing on those bodies which basically have those three conditions. Um, the first one was the chemicals for life, and the second was the energy for life, or swap those two in one. But the third one, which was the primarily important one, was the transport medium for metabolism to take place, and that, of course, would be liquid water. So we were going to talk about places where there are chemicals, there are energy, and there particularly is liquid water. Though in the case of some of these bodies, the liquid will not be on the surface. It will be underground or under a ice pack. Excuse me. So with no further ado, let's talk about our learning objectives for this module. Um, the moons of the outer solar system are going to primarily be focused around Jupiter. There's a series of Galilean satellites, meaning they were discovered by Galileo about 400 years ago in 1609. And we're also going to talk about some of the moons around Saturn, and I'll give you a little tour of which moons those are going to be in the next slide. We want to sort of support the idea of why that we think there might be life on these bodies, but I guess that's a little too strong. We just want to discuss their habitability. Okay, so we will discuss evidence for an ocean, an underwater ocean around Europa, and there's one of the good movies, videos on that, and discuss that if Europa could have life. Again, that's going to be discussed in greater detail in one of the videos. And are there other moons? And the answer is possibly yes. So life around Saturn, the moon that we're going to talk about is Titan mostly, and then we'll talk about some of the other moons as well, particularly just one other one in some detail. And then there's a moon around Neptune, which was actually captured by Neptune, and we'll talk a little bit about that later. And it has also evidence for some atmosphere and liquids that are active. Okay, so beyond that, we'll do a little bit of a summary at the end and talk about exactly what it is that why we favor these particular modes. Now this slide is showing you some of the relative sizes and properties, I guess you will, in terms of their visual images of some of the moons in our solar system. On the upper left, you can see Earth's moon, and you can see its relative size. And so, interestingly, if you move to the right, you see Mars's moons, and you may have to squint. There are two very small moons that are believed to have been captured. Then we do have little asteroid objects that are that have moons, and so this is one of them. Ida is mentioned here. But when you get to the Jovian planets, Jupiter, Saturn, Uranus, Neptune, you really start to see full systems of moons. Okay, and it's pretty spectacular how many moons Jupiter and Saturn actually have. So around Jupiter, we're going to concentrate on Io, Europa, Ganymede, and Callisto. And you can see them from top to bottom there in the image, and their relative sizes to the moon. So they are large moons as far as moons go, but you can see relative to the size of the Earth, they're still quite small. Then we will talk about the moons of Saturn. And even though there's a lot of moons to talk about with Saturn, and each of them having their own interesting geological oddities and uniquenesses, we're going to focus on Titan and Enceladus. Now, Titan has always been a very, very interesting moon in many ways because it very much has a thick atmosphere. And we're going to find out later that it actually has liquid methane, open bodies of liquid methane on its surface. The only other solar system object that we know of that has liquid pooled on its surface, and especially in vast quantities. Enceladus really hit the news more recently when it was discovered that it has a huge reservoir of water geysers that are coming out of its south pole and are actually responsible for creation of the E-ring around Saturn. Uranus we'll stop by, take a quick look at, we'll do a flyby, so to speak, but none of those moons really are going to make our radar list as far as having the three requirements for life that we discussed. And then we'll stop at Neptune before we sort of head out to Pluto and beyond. And with Neptune, it turns out that there was a moon that was captured. I should say it was a body of its own right that was captured and became a moon of Neptune, and it's called Triton. So we'll give Triton a small discussion as well. Now we know that one of the most important requirements for life is the energy for life. So we're going to talk about where does the energy come from for a lot of these moons. Now, with Earth and in the inner solar system where the planets are closer to the sun, the sunlight can actually deposit a great amount of energy, enough energy that you have enough energy budget to drive a lot of atmospheric and geological behaviors that life can tap into. And so the sunlight is really a major source of energy for the inner planets. But as you go further out, remember that Jupiter is 5 times further from the sun than the Earth is, which means it gets 1/25 as much light energy. And Saturn is 10 times further. So it gets roughly about 1/100th as much light energy as the Earth. And Neptune is about 20 times further, and so it gets about 1/400th as much light energy. So if there's very little light energy really coming down, being captured by these moons that are orbiting around these larger Jovian planets, then where is the energy coming from? And the energy, it turns out, is coming from something called tidal forces. And tidal forces are related to gravity. And as you know, gravity is one of those forces in nature that is stronger when you're around a more massive body. And it's also stronger when you're closer to the body and weaker when you're further from the body. In fact, it also obeys an inverse square law as well. So if you're twice as far away from Jupiter than, say, I am, you will experience 1/4 as much of the gravitational pull on you or force. And so it turns out that when you compare the gravity from, say, the moon on the Earth, that as the moon goes around the Earth, it's always above some location on the Earth, and there's always some location that's on the other side, farthest from where the moon is. And so you can see in the upper right-hand picture, here's an example of that. So you have the moon, it's pulling gravitationally on the Earth, and the black arrows are indicating the strength of that force. And so the near side of the Earth, of course, is experiencing a stronger gravitational pull from the moon than is the center of the Earth, which is also experiencing a stronger gravitational pull than the far side of the Earth from the moon. And you have to remember that the moon is orbiting around the Earth, and you have to remember that the Earth is rotating on its axis. So there's a lot of dynamics involved with this, but the fact of the matter is, whatever direction it is to the moon, that part of the Earth is feeling a stronger force than the opposite side of the Earth. And believe it or not, it's not it's kind of a strange phenomenon, but this actually ends up causing a stretching effect of the shape of the Earth. So in fact, that there's sort of this bulging that happens on the side of the Earth that's closest to the moon or directly underneath the moon, and there is very, very not a bulging, if you will, happening on the far side of the Earth, or I should say that the stretching is the least. And so that's being showed by this sort of blue oval that's around the Earth. That in fact, what's happening is that the Earth is feeling um, this force in a differential way across it, and that's causing this stretching, which is exaggerated in this light blue image around the Earth. And this phenomenon is called tidal forces, and basically it is a differential gravitational force, meaning that there's a difference between the front side and the back side of a planet relative to another object's location and gravitational pull. So anyway, in blue writing there, you can see that I said that this is called a differential force, and I've underlined it. And the net effect is that it can stretch the planet, or in case of a moon around a larger planet, it could stretch the moon. Okay, and so these tidal forces will vary in time, and they vary in time because of what I said before, which is the moon is orbiting around the Earth, and the Earth is spinning on its axis. And so at any location, at any time, as the Earth spins and you get carried underneath the moon uh, along the Earth's surface, then you feel the tidal force the strongest when the moon is directly overhead, and it gets weaker as you pass on by. Okay, and so this really, because the Earth is solid, it tends to bulge. The bulge tends to rotate out from underneath the moon, and this causes a sort of backwards torque toward the moon on the Earth. Now this is shown in figure 9.8 down at the bottom, as you see that the exaggerated elongated shape of the Earth, the bulging of the Earth, has now the rotated, that's what the blue tilted arrows are showing, that the major axis of this elongated bulge has rotated out from underneath the moon. Even though the moon is orbiting, as shown to the very right there with that gray arrow, its orbital motion is very, very slow relative to the Earth's spin, and so the Earth does really carry that bulge, further away from the direct line between the Earth and the moon as it's rotating. So this sort of causes a torque for the Earth to want to slow down, actually, or if you will, it causes the bulge to have to move back underneath where the moon is, and that causes a friction when the ground has to stretch like that and then come back down. That actually heats the ground, and that causes that is an energy that is generated, and there's a payback for that. Energy is conserved. And so what happens is that the Earth's rotation is slowing down ever so slightly with every single time that this phenomenon is happening, which it's a smooth, continuous phenomenon. Back in the day, the dinosaurs, the Earth rotated on its axis every 18 hours. Okay, and now today it rotates on its axis every 24 hours. So it has slowed down that much in the last 200 million years. So that's one thing that happens is you get you get heating of the planet, and you get a slowing of the rotation of the planet. Now, if that is enough, there's one more thing I have to tell you. The moon also because energy and rotation energy are all conserved, the moon is also changing with time a little bit. First of all, the moon, because of its tidal experience with the Earth, a long time ago, its rotation slowed down to the point where it basically stopped. And that is why we always have one face of the moon facing the Earth. And that's called synchronous rotation, and I'll get into that in the next slide. But an important aspect that I need you to learn here is that the moon is also slowly moving away from the Earth with time. Because as the Earth slows down, you have to conserve the overall rotational angular momentum of the Earth-Moon system. And so what happens as the Earth slows down is that the moon will move a little bit further away, and that's part of how it conserves angular momentum. And the moon is moving away from the Earth at about something like 2 centimeters a century right now. That's measured very precisely. So the Earth's rotation is slowing down, and the moon is slowly moving away from the Earth. And this is a process that's due to tides. And the Earth gets heated by the friction of the tidal effect as the bulge is being pushed around or moved around the surface of the Earth. Okay, this last bit is called tidal heating, and it's going to be a very key point to what heats and keeps the moons heated around the Jovian planets. Okay, so you have tidal heating, and that is the warming of the body because of the stretching and pulling of the bulge as it rotates underneath the line of the force of gravity from the other body. So with tidal heating, the body gets heated up and warmed, and that's a source of energy. And the other thing that happens is because, as we were talking about, the friction is causing the heating, that the friction actually slows the planet's rotation down. So let's consider a situation where you're walking around, say, a ball. So this is the left-hand picture labeled A. Let's say you walk around a ball, and as you do that, you don't change your direction at all. So that would be basically no rotation. You can see this young lady here and these 4 cardinal points along the orbit. She is not rotating whatsoever, okay? Now, obviously, you can think of if she was rotating very, very fast as she walked around that red circle, then that would be a very fast rotation rate around her axis as the other extreme. Now, due to tidal heating, that fast rotation would slow with time. And what happens is the one face of the body would get then frozen in the direction toward the central body. And so in image B, you can see our young lady is facing the central ball. Let's say in the top image she's facing, but as she walks along the red circle in a counterclockwise direction, for example, she would have to rotate at a rate that's identical to exactly her orbit around the central ball, and she would continue to face the central ball. And so she's rotating on her axis, but you have to see that she's rotating on her axis that's exactly timed with her orbit, such that she's always facing the central body. And so this is called synchronous rotation. It's a 1-to-1 ratio in which the rotation of the body on its axis, in this case the young lady, is exactly identical to the location, is exactly identical with the orbit. So that there's a 1-to-1 ratio, and you are rotating, the body is rotating, but it's rotating perfectly in sync with the orbit so that it only has one face facing the central object. And we're going to find out that nearly all of the Jovian moons exhibit synchronous rotation. And this means what? This means that they have been experiencing tidal forces for a long time, just like our moon has. Now, our moon stopped rotating because, it's a small body. It doesn't have a lot of internal energy. And so it basically experienced stronger um, um, impetus to slow down, and now is facing the Earth. The Earth has a lot more inertia because it's more massive, and therefore it's taking more time to slow down, but it too has been slowing down in its rotation. In the case of the moons around Saturn, the moons around Jupiter, most of them that are in close, for example, are caught in synchronous rotation. Now, just so you have it for record, our moon is a synchronous rotating body. It always has one face facing the Earth. Okay, so that's the second to last fact there on this slide. Okay, and if you see a moon or an object that's in synchronous rotation, you definitely know that tidal forces have been acting on it for a very, very long time. Okay, and so that is one of the tall tale signs of tidal forces are in play, is the presence of synchronous rotation. So we come to our first moon that we're going to discuss in some detail around Jupiter, and that is the moon of Io. And we're going to talk a lot about the fact that it is experiencing significant tidal heating and is locked in a synchronous rotation. Okay, so first of all, let's consider the fact that the moon is in synchronous rotation. Therefore, it always has one face facing Jupiter at all times. Now, the second thing that we have to consider is that Io has a highly elliptical orbit. Okay, it's not circular, but elliptical. This means, as you can see in the diagram to the right, that when it's at the closest approach to Jupiter, it's experiencing gravity more strongly, and therefore also the tidal effect of the tidal forces is also much stronger. Okay. Then later, as the moon goes around its orbit, we're going counterclockwise, for example, we get to the farthest point from Jupiter, and it turns out that the gravitational forces are weaker, but also the tidal effect, the tidal forces on it are weaker as well. So what does this mean? This means that this poor little moon is like Play-Doh in Jupiter's hands. It's getting pulled and squished and pulled and squished. Actually, not squished, I should say it's being pulled and then not pulled as hard, and then pulled and then not pulled as hard. So when we're at the closest approach to Jupiter over on the right, you can see that the picture they've shown there is like a football. I mean, the moon is really being stretched out by these very strong tidal forces. First of all, Jupiter is incredibly massive, so the forces are strong. And second of all, Io is in pretty darn close, so the tidal forces are very strong. And so there really is a significant, you know, pulling on Io. Then Io moves away. It goes around its orbit. It gets to its farthest point from orbit, and now it's not stretched as much. It actually can come back a little bit more to a round configuration. And so you can effectively think of Io as sort of breathing in and out as it gets stretched when it's close to Jupiter, and then sort of goes back to round as it gets far from Jupiter, and then moves back close to Jupiter and gets stretched again. And this is just basically a sort of a breathing effect that's happening with Io with every single one of its orbits. And this is causing a lot of friction in its interior and is causing a lot of heating. So it turns out, even though Io is in a geosynchronous orbit and is, I shouldn't call it geosynchronous, sorry. That means that it's synchronous with the rotation of the Earth. I mean to say that it's in a synchronous orbit or rotation. And so that means that basically it always has the one face toward Jupiter. So apologies for the misspeaking there. Now, because of even though it's in a synchronous rotation where it has one face facing Jupiter all the time, so it doesn't have this rotating bulge effect like that's heating the Earth in its particular configuration and dynamics. It turns out that because of the highly elliptical orbit, it gets stretched when it's close, and it gets allowed to go back to round when it's far. And this causes the heating. Okay, so I think I have that down in the lower left there that's continually being heated by the internal friction of these tidal forces. And we're going to find out that the same thing applies to the other moons, Europa, Ganymede, and Callisto, which are also orbiting around Jupiter. Okay, welcome to what is probably the most comprehensive slide of the slide set for this lecture. I hope your mind is fresh because I'm going to have to explain a few things here. Just to review, we've talked about tidal forces, and we've talked about tidal heating due to tidal forces. And one of the things that we explained was that if a moon is going around a central planet or body, that that central planet is going to also experience some tidal forces as it's rotating on its axis. And that is going to cause some heating of it as well. And it's going to lose energy to that heat. It loses rotational energy to that heat, so it slows down. So the inner planet, the central planet, is going to, rotation is slowly slowing down. Now, to conserve all quantities, that would mean that the moon itself will slowly be moving away from the central planet. And so we saw that that's happening with our moon. Our moon has gone into synchronous rotation. It is locked with one face toward the Earth, and it is slowly moving out in its orbit as it causes the Earth's rotation to slow down very slowly. Slowly rate of the slowing down over time. And so as the Earth's rotation slows down, the moon is slowly moving away. And so that would be expected to happen around any planet, even Jupiter. So if you have Io here, for example, the inner moon, and it's locked synchronously, just like the moon is around the Earth, so one face is always facing toward Jupiter. Jupiter is going to be exhibiting feeling some tidal forces as well from the moon, and its rotation then be slowing down slightly, and Io would be expected to move away with time, slowly, of course. Now, over billions of years, that can be significant. For example, the moon, over billions of years, has moved away far enough from the Earth that, in fact, it feels hardly any tidal forces from the Earth anymore. And so the moon is really not being tidally heated anymore and became a cold, dead body. Now, Io, it turns out, is not a dead geological body, and we'll talk about that in the next slides a little bit more. And it is experiencing significant tidal heating still today. Now, what I was trying to say with all this is that if a long time in the past, say around 4 billion years ago, Io was experiencing a lot of tidal heating, and Jupiter is experiencing some tidal heating, that Jupiter would slow down, Io would move away, and eventually it would be like the Earth-Moon system. Io would have moved away far enough from the planet that it would not continue to experience tidal heating, and then it would cool off and become a cold, dead moon. So for Io to continue today to still be tidally heated means that something has stopped that process of Io moving away with time. Some other physics is going on that has stopped Io from moving away with time, and so that Io now, even 4 billion years later, is in that same orbit and is still being tidally heated. And that is an important aspect of what we're going to be talking about with this slide. That phenomenon happens, the phenomenon where orbits get fixed with cosmic time like this, happens in multi-moon systems, okay? And it happens because they set up something called an orbital resonance. So that's what this slide is about, orbital resonance. And I've tried to tell you the significance of orbital resonance is that it holds the moon in its orbit so that for billions of years it can be tidally heated. And that means you have sustained energy input for billions of years, which is one of our requirements for life to have developed and evolved. So that's why orbital resonance is important. to our discussion. Now, how does it happen? Well, the best way to describe how it happens is to give you an example of Europa, because Europa is in the middle, and so it's easy to illustrate. Now, Europa is moving around the center lane, and Io is moving around the inner lane, and Ganymede's moving around the outer lane. Okay. Now, the closer you are to a planet, the faster you move along your orbit. So Io is moving the fastest, Europa the next fastest, and Ganymede relatively the slowest. So let's look at the alignment now. Europa and Ganymede aligned. And so what happens is, because they're close together, their gravitational influence on each other is at its peak. It's the strongest. And what happens is that Europa is kind of trying to pull Ganymede in, and Ganymede is trying to pull Europa out. Okay? Now, if you could imagine these planets rotating around in the direction of the arrows counterclockwise with time, you could imagine a time when Io comes along the inner lane faster and catches up to Europa, and now Europa and Io would be aligned, if you can imagine that in the picture. And when they are, now what do you have? You have Io kind of tugging Europa to a lower orbit inward toward Jupiter, and Europa tugging Io kind of outward into a further orbit from Jupiter. And so what happens is, Europa, whatever orbit it started in, it gets pulled inward by Io, and it gets pulled outward by Ganymede, and it's kind of this pulsing thing that happens every now and again. And eventually what happens is Europa will find an orbit between the two of them in which it locks into resonance, and it gets pushed and pulled and then pushed and pulled in such a way that it stays in the same orbit. It's in actual resonance. And this happens when the time period of the orbits are multiples of each other. For example, it turns out that for every 4 orbits that Io makes, Europa makes 2 orbits. Okay? And so this is called a 2-to-1 resonance. Basically, every time Europa has gone around 1 time, Io has gone around 2 times, and I'll show that in the next slide. And also there's a movie which shows this, which is on the website, and it has to do with a really cool beat that every time that Io and Europa align, it's sort of like a snare drum sound, and then every time that Europa and Ganymede align, it's kind of a bass drum sound, and then every time Io and Ganymede align, there's sort of this synthesizer sound, and so you get this, beating like and it's like you can feel that it's like a musical beat. The ratios of these planets' orbits, and so they first show it very slowly, then they speed it up, and pretty soon you've got sort of this hip hop beat going. It's kind of cool. You must really watch that video, and then you can see the resonance going on. And just remember that this resonance is what locks these moons into their orbits. So they didn't start in these orbits, but they influenced each other until they got locked into these orbits. Okay? So let's just recap real quickly. Moons would naturally move away from their central planet with time. Okay? And therefore their tidal forces acting on them, the tidal heating, would decrease until the planet was far enough away that it would cool off and become cool and dead. But when you have multiple moons, you get resonance orbits. The moons get locked into place. Therefore, they are experiencing those tidal forces and the tidal heating basically for all time until, for some reason the system gets destroyed. So resonance orbits are important because they allow the tidal heating to take place for billions of years, and therefore keep the planet or the moons geologically active and heated. Okay? So, in that sense, the resonance orbit phenomenon resolves the problem of the moon moving too far away that it cools off and becomes dead. So this is a good time for me to mention some of the videos that we have for this module. The first one was zooming out from Jupiter, showing its moon orbits. It's about 33 seconds, and it's really quite good. It lets you see that there actually are some moons closer to Jupiter than the four Galilean moons that we've been discussing. And it shows you how close they are to Jupiter relative to the dozens of other moons that are there. So it's really a nice little watch. And then, of course, there's a little video on the bottom of this slide that you could watch. It's silent, but it shows how the orbital resonance that's described in this picture here, a 2-to-1 orbital resonance. But for fun, video 2 is called Orbital Resonance of Jupiter's Moons Set to a Cool Beat. And it's really quite cool because they make a different sound every time two of the moons align. And they start out slow, and then they speed up the video, and all of a sudden, you've got this cool little hip hop beat going, and you can watch as the different moons align. Each alignment has its own sound. One's like a snare drum, the other one like a bass drum, and it's really quite cool, and it really illustrates orbital resonance beautifully. So if you want to see it in action and hear it, and sort of see that nature is quite musical, actually, in a natural way. Or I should say, music is very much mathematical. It's a very cool little video, and it's only a minute. So I really recommend that you watch those videos. Okay. So let's go back to this slide. This is an example of a 2-to-1 orbital resonance between Io and Europa. You have Io in the inner orbit, or the inner track, and Europa on the outer. And so you can see in the panel labeled 1, they're aligned at the beginning. And then as we go to panel 2, Io has gone halfway around its orbit so that it's at the top, and now at the farthest distance from your Jupiter. And you can see that Europa has only gone a quarter of the way around. Then we go to number 3, and we see that Io has made it all the way around. It completes its first orbit in this set of cycles, and you see that Europa has made it halfway around its orbit, and now they're opposite of each other. And then, of course, you go to panel 4, and Europa has gone 3/4 of the way around its orbit, whereas you see that Io has done 1.5 orbits, and it's back to its farthest approach from Jupiter. And then on step 5, we see that they're both aligned again, that Io has come around, made 2 complete orbits, and now we finally have that Europa has made 1 complete orbit. And this cycle just repeats itself, 1 through 5, 1 through 5, 1 through 5. You could watch it like a movie, and in fact, that's what the little video at the bottom of this panel shows. And you can even see it much more cool because they do it with 3 moons. They include Ganymede, and they set it to a beat. So a very fun video. You should definitely watch it. So at this point, I've kind of talked to you a little bit about Io and Europa and Ganymede. I haven't really mentioned Callisto. I haven't really introduced these moons to you as the separate entities that they are, and the interesting facts about them. So far, we've just talked about the phenomenon of tidal heating and the phenomenon of resonance orbits, and how the two of those combined give you sustained heating of the planets, or I should say the moons in this case. Now, it turned out that it was actually in 1609, not 1620. It wasn't exactly 400 years ago. It was 400 years ago in 2009 that Galileo discovered these moons around Jupiter. There's a picture of his original scribblings, if you will, or his scientific notes that he showed. And it didn't take him long to realize that these were bodies that were actually gravitationally bound to Jupiter. Of course, he didn't understand what gravity was. That took Newton and the invention of calculus to put all that together. But he did understand that this implied that you had another central body about which another system, separate system in its own right. And this, of course, got him in trouble with the church when he talked about that, because as you know from the beginning of the course, Galileo was a big believer in Copernicus's heliocentric model, which was blasphemy and heresy for the church. And Galileo went through the Inquisition. He had to recant his beliefs, and he was held under house arrest for the rest of his life for basically believing that the sun was at the center. But as you know, Venus really helped him. The phases of Venus helped him believe that, and the moons around Jupiter helped him believe that. Okay. All right. So Io on the left. Well, here's the magic word, folks. The magic word is pizza, because Io looks like pizza. And in fact, there's another video on Io called Jupiter's moon Io erupts, in which the announcer says that it looks like pizza. And it does, as you can see. And this moon experiences so much tidal heating that it is the most volcanically active body in the solar system. And it has huge lava beds that are greater than, say, the size of the Great Lakes. And it's spewing all types of gases through these volcanoes out into space. And it's very interesting because this causes a torus to follow basically a donut of ionized charged particles of plasma follow Io around its orbit. So its orbit actually is this sort of ring of charged particles that have been stripped off from Jupiter's strong magnetic field from the atmosphere of this outgassing of Io. It's a very interesting phenomenon about Io. The next moon on the right is Europa, and Europa is very much the sweetheart of the solar system as far as water goes. Believe it or not, this small moon has more water on it than does the planet Earth. So if we need to go find some water, you know where to go looking. This moon, also tidally heated, also locked into resonance orbits, is our best candidate for a place where you may find life elsewhere in our solar system. And we'll talk about that coming up. Then you have Ganymede. Ganymede is the third moon away, and this is a very interesting body that also seems to have some liquid water underneath its surface. And Callisto. Callisto is an interesting body that is what we say is not differentiated. We'll talk about that. Its composition, meaning its composition is uniform throughout. It's not like other bodies where the heavier elements have sunk to the core and the light elements are toward the surface. But there's evidence from an impactor that Callisto also is kind of mushy and may have a sludge or a liquid ocean underneath it. So we're going to take a little tour of each of these bodies in the next few slides. This is just a quick slide of the four moons of Jupiter. If you look at the top right, you can see Io, the inner moon, Europa, the second, Ganymede, the third, and Callisto, the fourth. This is just to show you relative to the size of Jupiter, what the size of these orbits are, and how far the moons are from each other. And I want to remind you that they are in resonance orbits. So for example, for every twice time that Io goes around, Europa goes around once. And I think Ganymede might be in a 7-to-1 resonance with Io or something like that. It's moving much more slowly. Callisto is not quite yet in resonance with the other moons. So it takes time to get into resonance, and it turns out that 4.5 billion years wasn't enough for Callisto to quite get there, but it's on its way. Okay. Now, if you look to the lower left, you'll see that there are a few moons that are actually inside of Ios. So in this case, the outer orbit is that of Europa. The next one in is Io, and inside that are four other moons. And I just wanted to bring that up to you, that there are these four moons that are in closer than Io. They must be experiencing just an intense electromagnetic soup from Jupiter's gigantic magnetic field and tremendous tidal forces from Jupiter. We really don't know any details about these moons because we haven't been able to actually get any spacecraft in close enough to Jupiter to give these guys a real probing, if you will. Okay. Let's see. In the lower right is a smorgasbord of all the different moons that are known around Jupiter, and you can see that the orbits are crazy, and many of these moons are captured. They were not, say, coeval with the formation of Jupiter. What I'd like to do is have you watch that movie again, zooming out from Jupiter, showing the moon orbits. It's only about 30 seconds long. This is the link to it here, but again, it's on the module, and it really does give you a feeling for how chaotic and how busy is the area around Jupiter. Heading back to the lower left again, in the magenta is the ring um, of Jupiter. And so Jupiter has a ring. Now, when I was a young kid, we were in school. We didn't know that Jupiter had a ring. It wasn't until the Voyager 1 spacecraft flew past Jupiter that it actually took images and saw the ring. And this is an example in the right, a red line showing the trajectory of that spacecraft. So here's the moon that sometimes when I'm talking to young kids, I call pizza face for fun. And this, of course, is Io. And what I'm showing you in the black and white photo to the left is from the Voyager spacecraft. It is the discovery image of the first volcanic plume on any other body besides the Earth. It was discovered around 2 a.m. by a young woman who was a PhD student, and she was alone at the control center as the images came in, and she was looking at these as they came in, and she squinted her eyes and thought, what the heck is this? And of course, realized what it might be, called up some of her superiors, and they came in, and lo and behold, they had discovered volcanism on the moon of Io around Jupiter. I have a small 2-minute movie that definitely is very cool. It's called Jupiter's Moon Io Erupts. I definitely want you to watch that. That's video 3. And a more modern image that was taken from the Galileo spacecraft, which was an orbiter around Jupiter, shows this same volcano exploding from basically the same angle with a higher resolution imaging. And so you can really see that we improved from 1979 to 1995, but it turns out now that the spacecraft is able to sniff out the different elements and measure the magnetic fields and do all kinds of things that the Voyager spacecraft was not able to do. You see that the surface of Io is constantly being repaved, and one of the reasons that you see so much yellow is because it's heavily coated with sulfur and sulfur dioxide deposits. And there actually are burning lava fields, as you can sort of see in that one image down there at the left, if you will. So it's just basically heat-like energy coming off of these lava fields. So what I failed to mention in the previous slide was that the habitability of Io is pretty low. It does have the energy. There is no doubt about it, it has the energy. And it has the chemical elements for life. There's no doubt about it. It has the chemical elements of life. So that's 2 out of 3. What it is lacking is liquid water. It is an extremely hot, extremely arid body. And in fact, there's no chance for there to be liquid water on the surface. The environment is way too hostile. The temperature is hot, and you're in a strong magnetic field where you have atoms being basically torn apart into their component pieces and ionized. And so it's a very, very hostile environment, and it's very doubtful that life would have A, formed, or B, would survive if it was on Io. So I forgot to mention that in the last slide. even though it has two of the three criteria for life. But this is Europa, the second moon out, and Europa is a different case. Okay, the tidal forces acting in Europa are about 1,000 times stronger than that acting on the moon Earth system. So it's quite strong. And this causes it to be continually also breathing in the same sense that you see Io breathing. Okay, getting heated, staying warm inside. Okay. Now, there's a couple things about Europa that would suggest that there's evidence for an ocean. There's a small number of craters, and that means that the surface is being repaved all the time, that it's a young surface. So something is happening that is basically smoothing out the surface with time. Okay, number two, there's chaotic flooded terrain, and if you take close-up images of these areas, they look very similar to the chaotic flooded terrain on the planet Earth. It's definitely icy skin that's got liquid underneath it, okay? And so the repaving would be some of this liquid coming up through the cracks and then flooding into floodplains. Okay, and it turns out that there's evidence that there is somewhat of a small internal magnetic disturbance around this moon, okay? And that doesn't mean that it has its own internal magnetic field necessarily, but you know, it is embedded in Jupiter's magnetic field. And that means that there are these strong magnetic field lines that have to be disrupted from Io's presence. Now, if Io was inert and didn't have any conducting capability at all, electrical conducting capability at all, those lines would just basically bend right around it and there would be no problem. And that's sort of, I'm sorry, those lines would go straight through and there would be no disturbance of them whatsoever if it was not able to conduct electricity at all. So what I'm showing in the lower left is what would happen if it was highly conductive, you know, like a metal ball, which is highly conductive of electricity. When you put magnetic fields aligned, they actually bend around the conductor itself, if it's an electrical conductor. So we were able to measure the behavior of the lines as they passed through and around Europa with the Galileo spacecraft. And in fact, what we see is a map that you see on the right there, where it says Europa inside the blue circle, and it has all the lines that are heading from the lower left to the upper right. And so if Io had no electroconductivity at all, those lines would just be uninterrupted. But as you can see, there are these two areas of highly disrupted lines where they come closer together and are compressed. This is very much indicative of what happens when you have a conductor that all the conduction only takes place near the surface, okay? And the rest of it is fairly inert. So the surface basically blocks out the lines and then causes this sort of focusing in the direction of the lines of the external field, in this case Jupiter. So this is indicative of motions of electrically charged particles that move around the surface underneath Europa's ice skin. And what we believe this is that the water there is a briny ocean. Briny meaning very salty. And salt is made of sodium and chloride ions. And ions are able to conduct electricity. And so basically the salt, the ionized salt in the water is creating this disturbance in the magnetic field. So that's a very, very strong yet indirect indication of a briny subsurface ocean in Europa. Okay, and if you do the calculations, those calculations of the heat budget from the tidal heating is that there's a sufficient energy that the internal area of Europa is warm enough. It's in that 0 to 100 degree range that liquid water can actually survive and be sustained. Now, this slide is talking about older evidence from the mid 90s, the development of this kind of logic that we think this body has an underground liquid briny ocean. Now, I want you to watch the video Life on Europa, and in fact, you'll find out that new data from the Hubble Space Telescope have seen water geysers coming out of the South Pole of Europa. That's interesting because we're going to talk about Enceladus, a moon around Saturn, which has the same phenomenon, has these water geysers that come out of the South Pole. But Hubble Space Telescope has really recently been able to measure these things, and there's really enough energy that life could exist in this ocean. And so I'm going to show you some details about that, but you really will learn the most about Europa if you watch the movie Life on Europa, which is one of the PBS Space-Time shorts. Here's a simple model of what Europa looks like, as well as some close-up images showing some data. Basically, the big large image is an actual photograph, and then it's been overlaid with a model of what might be underneath the surface. And then you can see the insets of the spherical cutaway of Europa, showing a core and a mantle, and then the subsurface ocean below the ice that is just below the surface. And you can see the little cutaway of that showing the ice cap above the top. And this ocean probably is believed to go down about 100 kilometers. Now, by comparison, the Earth's ocean only goes at its deepest about 17 kilometers. So the Earth's ocean is only about, at its deepest, 20% of the depth of this ocean around Europa. Okay. Now, the image on the upper right shows cycloidal ridges, and then I show a blow-up image of what those look like in more detail. It shows something called, a band. These are areas where you have some splitting, and you basically have floodplains from that splitting of the ice, and those are the areas that look very much like the frozen tundra on the Earth. We also have an impact crater. These are areas that are older or have been hit and not repaved over at any recent time. And then, of course, we have what are called chaotic areas, labeled chaos in this case. And again, if you look at images of the Earth, they really look a lot like this. So the idea that there's ice and water is highly supported. I want to say that people have used spectroscopy, if you remember that from a previous module, I think it was C6, that with spectroscopy you can determine what the chemical elements present are from their various fingerprints, the way they interact with the light. And guess what? It's water, folks. Okay, so they've seen the spectrum and they can tell that that's water ice, very much so. And when the Hubble Space Telescope saw the geysers, they took the spectra and they saw that it in fact was water. So there's definitely, this model is highly favored as a possible model. We won't know until we go there and somebody, in a sense, goes and dives into this ocean. We definitely want to send a probe. And there's been talk of sending a probe. You'll hear about it in the movie Life on Europa. It's called the Europa Clipper. There was great promise for this spacecraft. Unfortunately, in the 2020 budget, Trump completely cut off funding for it. So we're not going to be learning about Europa anytime soon. I don't know if you heard my heart break, but it broke my heart. Just to drive the point home, to give you an idea of how precious water is and how very little of it there really is on the planet Earth, here we have an image put out by NASA with Europa on the left. You can see its size relative to the dry Earth. And you can see there, if you removed all the water from Europa's underground ocean, which is believed to be about 100 kilometers in depth on average, and you were to pull it out of Europa and make a ball out of that water, that's how big it would be compared to Europa itself. The same thing now, you've got the Earth on the right. If you were to suck all the water off of the Earth and just put it into the shape of a ball, that's how big it would be. And you can see that is a smaller ball of water. There's less volume of water on the Earth than there is on Europa, and that's pretty amazing. So it turns out that it's not, I just don't know what to say. Earth really is precious in the amount of water it has, and it may seem like a ton of water, but it's really quite amazing to see that even a body as small as Europa could contain more water. And if we ever become interplanetary travelers or we become intergalactic travelers, finding these small moons might be more precious than rocket fuel or anything else, because water is basically the transport medium, the fluid of life. Here's a more modern image that shows some of the geysers, such as were discovered by the Hubble Space Telescope. And this is just a summary slide to discuss the habitability of this moon, Europa. And in fact, we want to remind you, number one, that it has the three key environmental requirements for life. It has energy, it has elements, and it has lots of water. What we don't know is whether the energy is distributed in such a way that life can exploit that energy. Now, again, in the Life in Europa movie, there's a very important discussion about where life may have arisen on Earth, and if those kinds of sites are present in the deep underground oceans of Europa, then there might be a chance that such ecosystems actually could be alive and well on the moon of Europa. Okay, it turns out that in that video they talk about whether it's the underground ocean events or the underground thermal events of energy coming up through the bottom of the ocean, or whether you might have some sub-ice critters as well, because as mentioned in the video, there's a great amount of life that's just underneath them. In fact, the major biosphere mass is underneath the ice packs around the oceans. Now, that may not be the case if there is life on Europa. It may be that it's more likely down in the deep parts of the ocean if they have these thermal vents, and they do a fantastic job of showing these thermal vents on Earth. It's spectacular footage that they have. Now, the question is whether there's also enough energy budget to really spread this all throughout the moon, and it's not well known. Bottom line is, Europa is the most favored location for us to look for life else in the solar system, and that's why the Europa Clipper was so exciting. And you'll see the story of how Congress actually increased the budget for this mission before Trump decided to stop the mission. Okay, so right, definitely Europa is worthy of being explored. So as I was saying, we need to send some probes. And one of the things that was the plan of NASA was to send an orbiter to find a landing spot. And so we basically are showing some artist renditions or illustrations of what that might look like to land on the surface. And then the idea would be to take some robots, have them dig through the ice, go down, and then swim along inside the European Ocean and look for some of these thermal events, and to see whether there was life that was persisting around these thermal events. Moving on from Europa, next up is Ganymede, the third farthest of the 4 Galilean satellites. This is also a very interesting moon in some regards. I've got a series of bulleted points about this moon. You see both young and old surfaces, and the dark areas, which are old, are the ones covered with craters. The light areas seem to have been repaved, and some have grooves. And as we've learned about these kinds of grooves, that these are typical of fault line fractures through which, if repaving happens, you probably have a fluid coming up through them. So these may have been due to water eruptions. Ganymede has its own internal magnetic field. Now, just to remind you, this does mean that Ganymede must have a molten, electrically charged molten material in its core that is circulating. And so this circulation is what generates this weak magnetic field. And it seems to be a dynamo-like field, as you can see in the little diagram in the lower left. The green lines are the actual intrinsic field, and they're symmetric about the center of the planet, whereas the black lines around it are the lines that are from the environment, from Jupiter's magnetic field. And so you can see that the two are interacting. And it's very interesting that this is happening in the core of Ganymede. We really don't quite fully understand what the interior of this moon is like yet, but with time, as with everything else, if we keep doing science, we continue to learn more. So it turns out that the young areas that may have been due to water eruptions shows the presence of salts, as if the water that came up through was another briny type of sea, as we found for Europa. It's larger than Europa, which means it can contain its internal heat better. It's further away, so it's not feeling quite the strength of tidal effects as Europa does and as Io does, but it still is being tidally heated. There's we believe the top is an ice layer that's about 150 kilometers thick. And if for some reason there wasn't enough energy budget for there to be life, it would probably be some very, very simple extremophiles, as we know them on Earth anyway, by that terms. But it would be probably localized to little energy spots and very, very simple. If there is life, we have no clue at this point. We have to really go out there and do the studies. I included this map because I really love the idea of a map that is incomplete. And so you can see that on the polar regions, you can see the black spots that indicate we have absolutely no data. And then you see these very, very crude maps of the entire surface based upon different terrain types. And these maps really remind me a great deal of the crude maps of the planet Earth that people were putting together in the 1500s and the 1600s. And there were these areas of gross misproportions of where continents were, how far they went, and there was terra incognita throughout various locations on the map. And I just love the fact that right now, when it comes to these moons, that we have sort of terra incognita, where we haven't even seen certain areas yet, as you can see from the black spots up there. In other areas, we have some high resolution imaging, but in other areas, we don't have any imaging. And so it's going to be very interesting to figure out what these moons are like and map them. And there'll be cartography for all the moons and planets in the solar system. So when people go out there, they'll know where to be. They'll use their fancy. It won't be GPS, I guess it'll be SPS for their solar system positioning satellites. Anyway, that's why I wanted to include this map. Now, as far as the habitability of Ganymede goes, that I mentioned briefly before that it probably would be very, very tiny areas that might have the energy gradients required for life to be able to exploit them. We certainly have the chemical elements. We certainly have energy, no, not huge energy budgets. And then we definitely have the possibility of a water ocean. So here's a diagram of the cutaway of our best understanding of Ganymede at this time. And you can see that we'd have a saltwater ocean and then sort of an ice-like area, and then a rocky mantle followed by an iron core, and then you would even have to have a liquid area to that iron core. The pressure being greatest at the center, making it be a solid iron core because liquids tend to go to solid under greater pressures, and the center has greater pressure on it. But you might have this shell around the core, which has liquid or molten iron, and therefore can create the domino effect for the magnetic field. And that could be somewhat protective to some degree. So anyway, here's a close-up picture of the grooves down at the bottom, so close-up picture of some craters, and then of some dark terrain versus the light terrain where you can see what appears to be a flowing or repaving of the surface. So definitely geologically alive at some level, and possibly strong evidence for some kind of saltwater-like ocean and iron molten shell near the core. Last but not least on our tour of the 4 Galilean satellites is Callisto. It's not quite yet in resonance with the other 3 moons. Its tidal heating would definitely be the lowest because it's furthest away. And we find out that this planet seems to be less geologically active than Europa and Callisto, and most definitely than Io. One of the things that we see is that the entire surface seems to be pockmarked and therefore appears to be old. We believe that underneath that surface is an undifferentiated mixture of ice and rock. There may be a mushy ice rock below the surface to some degree, and I'll give you some evidence for that in a minute. But the fact is that it does seem that the planet is not differentiated in the fact that it's kind of the same density throughout. You don't have the higher density in the center of heavier elements and then lighter elements toward the surface. Okay, and so this does imply that there isn't a lot of heat source going on. You know, that it basically solidified quite rapidly. In fact, may have formed by building up and being cooled off and then building up more and cooling off and being built up more. We really don't understand this moon very well at all. However, very much like Europa, it seems to have one of these induced magnetic fields. If you look at the picture down in the bottom, you can see the map of Jupiter's magnetic field around Callisto, and it does seem to have the characteristics of a surface current that's induced by Jupiter's magnetic field. And again, this would be suggestive of an underground, near the surface shell of a briny ocean around the planet. So that's kind of an interesting artifact, or I should say observation. And now I'm going to show you in the next slide some interesting evidence that, in fact, this planet does have sort of a mushy interior that may be a liquid or a liquid ice type of thing. So consider a large asteroid impact on a solid moon or a solid planet. If the planet really is quite solid, then that impact is going leave a scar on the side that it hit. But the impulse, the pressure of the impact is going to work its way through to the other side of that solid planet or moon and cause a bulge to emerge on the far side. Now, this is exactly something that happened with Mercury, because Mercury is quite solid. And what happened was with Mercury is it got hit by this impactor, and then it caused a scar from the impact, but on the opposite side of Mercury is a small bulge. Okay. Now, it turns out that Callisto has a huge scar on it from an impactor as well, a large impactor. And this is called the Valhalla crater. And you can see a picture of it right here. In fact, there was a clear image of it in the previous slide as well. What's interesting is if you do the mathematics for the solid body, given the density and the size of this planet, you should detect a bulge on the other side if the planet, or I should say the moon, was solid all the way through. And in fact, there is no bulge on the other side. And so that means that something about the interior is mushy and that shock wave was absorbed before it actually could propagate through to the other side of the moon. Okay. Again, this is consistent with some kind of underground fluid or mushy ice interior to the ocean, of an ocean, underground ocean. And the fact that is more supportive of an underground ocean is the fact that there is that induced magnetic field, which would mean that the salts, the ionized salts, can move around rapidly as induced by the magnetic field of Jupiter. So, no bulge on the other side of the moon from the Valhalla crater, which was due to an impact, indicating a mushy interior that shock absorbed that impact, and therefore evidence for a soft belly, if you will, and a water ocean underneath the ground. So here's our final comparison slide. First, we compare Ganymede to Callisto briefly, and then at the bottom, I compare all the 4 Galilean satellites very quickly in terms of their habitability. So when we look at Callisto, we see that on the right, we see that it has this mixed rock interior that's undifferentiated, fairly solid, with a water ocean, maybe a briny water ocean, and an outer icy shell. And with Ganymede, we see the same at the surface. We see the outer icy shell and a water ocean underneath it. And then we have an upper mantle, which is icy, rocky lower mantle, and then a partially molten shell around an iron core. And so Ganymede has its own magnetic field and certainly much more internal energy, whereas Callisto seems to be a very, very low energy environment. However, interestingly, enough energy that liquid water can exist under its surface. Now, in the past, we've talked about the temperature range of liquid water and the temperatures over which it's liquid. And that's 0 to 100 degrees Celsius. And that turns out to be true in particular environments, which we basically take to be standard temperature and pressure. And so, which is kind of like, the standard temperature, the standard pressure is sort of like an atmosphere. And you get the standard temperature of liquid water, 0 to 100, under those pressures. But under higher pressures, you can get liquid water at cooler temperatures. And so it may be that with these moons, that you can have liquid water in colder environments because it's underground where it's under a great deal of pressure. So that's something to consider. Now, with Callisto, we're going to have to say the habitability is probably pretty low. I mean, the energy budget is so very low, and probably not enough to really sustain metabolic processes as we understand them. Okay. We certainly have the first two requirements. There is some energy, and I wouldn't say maybe it's the first two requirements, but we have energy, we have water, we have low energy, and we definitely have the chemical abundances. But again, so very cold, such low energy budget, probably not underground thermal vents like we have a reason to believe might exist on Europa. So when we do a little summary down at the bottom from Europa, Io, Callisto, and Ganymede, again, I would say that the highest probabilities are in Europa. Then I would say that the lowest are on Io and Callisto, and then Ganymede, which has its own magnetic field and molten core, is a little bit more on the moderate side. So I can remind you that I don't have those moons in order of the way they are distant from Jupiter. That order is Io, Europa, Ganymede, Callisto, but they're sort of at random order down there. I just wanted to point that out to you. So that's our sort of habitability scorecard for the Galilean satellites. And in the end, Io, most geologically active, volcanically active moon, extreme tidal forces and heating. Europa, very strong tidal forces, a lot of water, more water than is on the Earth, and our highest probability for finding life elsewhere in the solar system. Followed by Ganymede, which has sort of a moderate possibility with an underground ocean, and Callisto, that even though it seems to have underground water, is probably very cold and likely to be lifeless. Okay, great. So we've wrapped up Jupiter, we've talked about these four moons, and we're going to move on to the Saturn system. And Saturn is another very amazingly active area of the solar system. A lot of captured moons, a lot of co-evolved moons. And in fact, there's this beautiful ring system as well, which we could spend a whole semester studying the majesty of that, its evolution, and what keeps it stable over billions of years. But alas, our discussion is going to focus on just two of the moons of Saturn, Titan, which is a very large moon and is the only moon or body in the solar system with open liquid on its surface. And then we're going to talk about Enceladus because it has water ice geysers that are coming out of it. Now, that's not to say that some of those other moons might be very interesting. And, in 10 years from now, if we send other probes out there and we study these moons, we might find some fascinating aspects about those which would elevate them to a discussion in a class like this. But just because we're leaving them out now, it doesn't mean that they're dead rocks that aren't going to be places that are of interest. Each one is its own world with its own geology and history, very fascinating in their own right, and we just don't know about them well enough to incorporate them in this discussion at this point in time. So here we have a mosaic comparing the relative sizes of several of the Saturnian satellites. And you can see that Titan is the dominant moon and it is cloud covered. And we're going to penetrate the clouds and talk about what's underneath it. And I guess I would like to maybe point out Iapetus is a very interesting moon. You can see a picture of it to the right of Titan there. And it's sort of one half pure white and the other half pure black. And interestingly, this turns out to be because it is being, in the direction that it's rotating, it is picking up ice droplets that are falling on its surface from space, and the other side is the natural black covering of the moon. And it turns out that those ice droplets are coming from Enceladus, and it's ejected water geysers that freeze. If you go to the lower image, you can see the relative distances of these moons relative to the rings. First of all, you can see that there's an A ring and a B ring, and they're separated by something called the Cassini division. Inside that is the C ring and the innermost D ring. And then you have something called outside the A ring called the Encke division, which there's a great deal of space, and some particles are focused into a very narrow band called the F ring, and then the G ring. And this is very interesting. We did not understand how that little bead or thin spaghetti ring could exist. For those who may have heard of something called shepherding satellites, it's a resonance phenomenon, just like the resonance phenomenon with the moons of Jupiter, where they've aligned and say Europa's and their orbital paths are fixed in a certain location. All these ring particles have been focused into this narrow band by two moons, one just on the inside of them and one just on the outside of them, that then focus these into a narrow spaghetti band ring. If you move out a little bit further, you'll see the E ring, which is this sort of nebulous fog ring. We didn't understand where that was coming from for the life of us until we realized that it's coming from Enceladus. And you can see Enceladus is smack in the middle of the E ring, and the E ring comes from the water ice particles that are actually ejected from Enceladus, and we'll talk about those. And then there is a movie that describes this as well, that's on the module. As you move out further and further, you can see as we get to the right of the diagram, Titan is actually off the right of the diagram, as well as Iapetus that I spoke of earlier. So those are actually outside the diagram, and you can get an idea of how far away Titan is relative to the rings around Saturn. Welcome to Titan. Titan is, as you can see in the bolded list, the second largest moon in the solar system. It has a very substantial atmosphere. It's even thicker than Earth's atmosphere. And of course, we've been boasting about the excitement of the methane lakes that exist on its surface. And I've stated several times that this is the only other body in the solar system with any kind of fluid on its surface. This atmosphere, which is clearly seen in the visible light image to the right, is kind of brown and smoggy-like. In fact, it's 90% molecular nitrogen, and like the Earth's is around 80% molecular nitrogen. But the rest of it is not oxygen. It is methane and ethane, and then a lot of other propanes. So basically, it's a huge deposit of, in a sense, rocket fuel and gasoline. And so, you could imagine that people might be very interested in being able to just basically siphon methane lakes off of this moon. Who knows what the industry of the future will involve, but there's a lot of energy contained in that fluid that if you oxidize it, you can release that energy. And that brings me to the question of, well, what would happen if you lit a match on methane? Well, nothing. It would go out. And the reason it would go out is because there's no oxygen on the planet that's in free form. So basically, it's a very stable situation for this moon. Now, the atmospheric pressure is close to Earth, so if you were to stand on the surface, you wouldn't need a pressure suit. You certainly would need something to keep you warm, because it's about minus 180 degrees Celsius, which is about minus 300 degrees Fahrenheit. This is a pretty damn cold, and you can imagine any chemistry that might take place would be happening at a very, very slow rate. which means it's not good for metabolism. And if there was any life forms there, they would be very, very slow metabolizers. My gosh, it makes me think that if life can exist in environments like this, we might not even recognize it as reproducible biology. Um, okay, so the inside of the planet itself is believed to be a silicate core and a mantle compressed of ices, and it's even believed to have a large underground liquid water ocean, like many of the other bodies we've been talking around Jupiter. There's less information on that, and I'm not going to be spending time talking about that particular aspect of Titan, but it's possible that this is another site which there's a great deal of water on the planet as well. But just to clarify, that water would be underground. So here are some images showing the methane lakes, where the methane lakes have been false colored to make them easy to see. And you can also see those areas of terra incognita where we haven't been able to map the surface and don't know much about it. And so I'd like to bring your attention to the size of these lakes. Okay, so this is the North Polar region. You can see that these lakes are surrounding this area. Now there's a red arrow with an image to the upper right with a red border, and you can see there is a comparison between one of the lakes on Titan and the Lake Superior and the Great Lakes on Earth. So that's just to give you a feel for the size of how large these methane lakes are. And with a thick atmosphere, such as Earth's, it's believed that winds will be taking place. And as you know, when there are winds across lakes, that causes waves. And so it's believed that if you are on the shorelines of these methane lakes, that you would see them actually rippling like you do with the Great Lakes, which is kind of interesting. It's always interesting to picture what it would be like to actually be physically on one of these worlds. Okay, one of the things that you may not appreciate about the outer solar system is that rock is something we think of as being made of silicates and these heavier elements on Earth, but that is true in the inner solar system, and that's because they are very, very solid at these temperatures, chemically bonded together. Well, the same thing happens with water when you get in the outer solar system. It can become very, very cold and become extremely hard. And so guess what? The rocks you're seeing in the lower right picture are actually water ice rocks. And these have been sculpted in a riverbed, just like our rocks get sculpted. So very interestingly, when the Huygens probe from Cassini went down and landed on Titan, it was able to take these photographs right next to it, and it had landed in an ancient riverbed, and these ice rocks had been sculpted in the riverbed in the same way that rocks on Earth get sculpted, and that was a fantastic realization and discovery about this moon. There's a little video across the bottom. I've actually linked it as video 5 in C9, the module 9. And I just want to say that about these videos, you'll notice that they're all sort of around 2 to 3, maybe 4 minutes long. And so I've really kind of carefully tried to find short videos that were not really highly time consuming, but gave a flavor for what's going on with these bodies. Because of that, some of them are a little bit dated or a little older. The graphics have gotten better with time as people have polished them. Some of these are shorts that were published very quickly to describe the excitement of the discoveries. And so I hope you'll bear with me that Not every one of these videos is the most modern, but it's so that you can, see only about 3 or 4 minute videos rather than watching a series of 15-minute videos or 30-minute videos, which I think would be quite burdensome. So I hope you'll enjoy that video of Titan. It's actually quite fascinating, and you actually can watch the probe come down and see the footage of the pictures it took as it got closer and closer to the surface coming through the atmosphere. So to give you just a small insight into how thick the atmosphere of Titan really is compared to the Earth's, I should say, in the sense that the pressure at the surface of the planet is similar to that of Earth's. And that's because the gravity um, of the moon is much smaller than the gravity of Earth, because it's a much less massive moon than the Earth is as a planet. It's smaller. Um, but you have so much thicker of an atmosphere in terms of the quantity of material. And so, even though the gravity is less on the planet, which is holding the atmosphere to the planet, there's so much more atmosphere that it balances out, and the pressure at the surface turns out to be the same or similar to Earth's. Now, if you look at the right hand side at the blue figure, it gives the height of the two atmospheres. And on the left is the Earth, and that scale goes from basically the ground all the way up to about 50 kilometers. And the temperature drops from about 290 degrees absolute temperature, which is, effectively your room temperature, but in absolute, on the absolute scale. And then it drops down to only about it drops down to about 210 as you go into the stratosphere, and then the temperature increases again, such by the time you get to 50 kilometers, you actually are in a temperature regime that is, again, a little colder than room temperature. However, of course, the pressure is very, very thin up there, so you can't just actually breathe or anything up there. And of course, you know that you get clouds. Clouds are really, really close to the ground, relatively speaking, down there at around 1,000 K to 2 or 3,000 K, and those then rain water down onto the Earth. And you can see that we have mountains that can be quite high as well. So if you compare that to Titan, Titan's atmosphere is about 10 times higher. So moving to the right diagram, you can see that atmosphere goes from ground level all the way up to about 500 kilometers, maybe 600 kilometers. So it's quite a bit higher, but they've squished this graph down so that it can fit on the page. And if you were to put the Earth's graph on top of the Titan graph, it would be squished down by that little blue line that I have way down to the 50-kilometer line on Titan. So you can see that the Earth's atmosphere is very small indeed. And over in Titan, you can see it's very cold, around 72 degrees Kelvin, which is about 200 degrees absolute temperature lower than it is on the Earth. And the cloud layers are actually up around 200 kilometers, which on Earth, that is in space. I mean, if you are going to take a ride on Richard Branson's Spaceship Two, or you're going to go up on Jeff Bezos's Blue Origin New Glenn rocket to have a quick trip to the space, then you're going to go up about 100, 150 kilometers. I think that's about right. And it might be 200 kilometers. It's somewhere in that range. And the point is that on Earth, you go that high, you're in space. If you go that high up in the atmosphere of Titan, you are at the cloud layer where the rain happens. So it's quite a different situation. Anyhow, um, you can see that it's more of a thick photochemical haze that exists up there in the sense of what we would have over the Los Angeles basin. And then moving up, you have more nitrogen, methane, and argon. So if we move to the left, it's basically a diagram published in a Nature paper describing the methane cycle that happens on Titan. We don't have any clue or have knowledge of whether Titan has plate tectonics. We just don't have enough data to know about the movements um, of any plates. But it seems that it does have volcanoes, and these volcanoes spew out water and methane, and it cycles through the atmosphere, collects into clouds, rains, collects in pools, in the same sense that the Earth has a water cycle. So it's kind of interesting in that way. Just it's I love Titan because it makes you really think about all the different planets and moons that are out there in the galaxy, and how different they all are, but how they all are so similar in so many ways in the way that they cycle certain fluids and have these processes taking place on them. This is our last slide on Titan. It's more about the interior. We mentioned earlier on our introductory slide that the core may be undifferentiated, and that it may have a mantle of ice, sort of an onion layer toward the top, and then a liquid water ocean underneath that. And then the surface is quite a bit of methane ice and water ice and ammonia ice. And then the atmosphere is very rich with these organic molecules, including ethane and methane and the other ones that we mentioned. Okay, so if we want to talk about the habitability of this object, well, let's see. It's definitely got the chemical elements, and I would say that the chemistry is alive and well. But the energy budget has got to be quite low. It's far away from Saturn, so it's not experiencing a great deal of tidal heating, and so that's one of the reasons why we don't think that it actually that it has an undifferentiated core, because it's not being heated and pulsated, and so it's not probably not being geologically agitated through tides with Saturn. So probably a very cold planet, therefore the energy budget's low. If you remember, Saturn is 10 times further from the sun than Earth, and so the sunlight energy that it's picking up is 1/100th of that on the Earth. Um, so in the end, we're going to give it a low score on the scorecard for life. Again, if there was some kind of reproductive chemistry that we might be able to call life, it would probably act at such a slow rate we would really have a hard time understanding that these things are alive. But like in episodes of Star Trek where they've gone to planets and they've eventually found that certain things are alive on these planets, even though they were completely new life forms that metabolize at rates that would be incredibly slow compared to humans. And of course, they've discovered in Star Trek life forms that metabolize so fast that they couldn't be recognized at first. So who knows what's out there in the universe? And if you chuckle at my bringing in science fiction, you just have to remember that science fiction, um, in so many cases, has become science fact. Uh, so it seems silly, but the fact of the matter is, as time goes by and humans go out into the solar system, go out into the galaxy, which I hope will happen someday, a lot of science fiction will become, in fact, science fact. Welcome to Enceladus, one of the moons also of Saturn, further out from, sorry, closer in to Saturn than Titan is. And this moon is spectacularly known and famous and well studied now because Cassini detected these water geysers shooting out of the South Pole. So you can see in the upper left image, there's images of those water geysers. And this turned out to be pretty fascinating. Once they took the spectra, they realized that in fact, were ice particles and uh, from liquid water. And one of the amazing things was that it explained the presence of the E ring, which you might remember I mentioned earlier in the lecture. And so in the lower left, you see in the light blue, the E ring is a very fuzzy and faint ice particle ring, which there was no explanation for until these jets were seen. And we have basically a closer up picture of them in the top center in black and white. And I'd like you to know that there's a lot of spectacular images now of these geysers that are up close and showing all kinds of details of the terrain from which they are jettisoned. But I'm basically going to show you a couple of artists' impressions. One showing Saturn in the background, what the geysers might look like, and then another one that gives you an idea of the underground water that would be involved in jettisoning these. Now, there basically has to be some kind of thermal energy that could be giving rise to this, and I think one of them is possibility is radioactive decay, which would be commonly found in all bodies because like I said, radioactivity is everywhere. There's isotopes that are unstable to decay, and they release heat. There, for some reason, must be quite a concentration of these in Enceladus, and there's a lot of enough energy to jettison these geysers out into space. Now, you can think about the thermal energy on the Earth and what's going on at Yellowstone National Park, but this is a situation where these geysers are so powerful that they go hundreds to thousands of kilometers out and escape into space and then get trapped uh, through magnetic processes into this gigantic E-ring. So this really is a sign of energy and organics and water. So this makes Enceladus rank in the sort of top three of the bodies in the solar system that are habitable in that sense of the three criteria for life. Now, I'd like to remind you that there's a lot of moons around Saturn and around Uranus and Neptune that we'll talk about that have not been explored in this level of detail. So it's a very alive solar system out there, and we're only highlighting the bodies that we've learned about. So this is a period of time where our knowledge is very incomplete, but exciting things have been learned, and now we're sharing them in the classroom with you. This is our beloved Cassini spacecraft, and the spacecraft spent almost a decade orbiting around Venus and had multiple different phases to its mission. It probed or flew by many of the moons. It flew through the rings, above the rings, behind the rings. It flew over the poles. And in fact, it sort of tried to stay outside of the ring system because it was dangerous. But in the end, Cassini was probably carrying biologics from the Earth that survived. And it also flew through the plumes of Enceladus. One of the things they did after they discovered those plumes was they directed Cassini to actually fly through them so that it could sniff out the particles and measure the organics in the water coming off that small moon. And so they didn't want to have, if there was any life in there, they didn't want it to contaminate any of the other moons or something by having Cassini accidentally crash into one of the moons and and deposit these possible biologics anywhere, especially the ones from Earth. So they basically decided to burn the spacecraft up in the atmosphere by having it go inside the ring system, which was very dangerous, but they thought they would give it a try. And so they did multiple orbits uh, using aerobraking, where they skimmed the top of the atmosphere to lose energy um, of the orbit, and eventually after so many times of going through this aerobraking process, um, then the spacecraft's lost enough energy that its final plunge will go into the atmosphere. It will burn up, much like satellites that come through the Earth's atmosphere do, and be completely obliterated. Anything that was alive on it was, heated to the point where it would be vaporized. So there was no question that this was the answer for Cassini, and a lot of tears were shed. And I don't say that as a joke. After people lived with this spacecraft for 20 years, because from the time it was on the drawing board to when it flew to the 10 years of directing it and being with it and commanding it and receiving information back from it, there literally people were in tears when it died. They had come to be family for some of these people. So anyway, here's Cassini by the numbers. You can see it had this tremendous top speed of 76,000 miles per hour. It I don't know. It did a tremendous number of things. So I just put that slide up there just to sort of talk about it. But if you're interested, you can read it. But I hope you'll watch the Death Plunge movie. It's a National Geographic plug for a longer video on Cassini that, if you're interested, you should definitely watch. It is probably the crowning achievement of all spacecraft that have gone into the outer solar system. So I hope you'll watch it. It's quite neat to see the computer graphic of how the spacecraft was torn apart going into the atmosphere. Now, I want to remind you that Cassini also, on its tail end, took the Huygens probe, and it had sent the Huygens probe down into the atmosphere of Titan, and it launched a parachute and landed on the surface, and that's where we got those surface pictures of Titan and saw the close-up pictures from the air, if you will, of the lakes of Titan. Welcome to Uranus, the next gas giant in our tour. Uranus has only been explored by a single flyby of Voyager 2 back in 1989. And as it passed through, it took snapshots of some of the larger moons and basically what are known as the 5 major moons. And those pictures are shown here in the inset of this diagram of the orbit and orbital locations. And in the very inner region, you can see that there are some rings around Uranus as well. So these 5 moons are the ones that we would probably like to study the most if we can have a Cassini-like mission around Uranus. And there are 13 additional inner moons, and then there are 9 irregular moons altogether. And we continue to discover more. I think in the next slide it shows a couple that were discovered by Hubble Space Telescope. But the bottom line is these moons could have water. They could have underground oceans. We do not know. We don't understand the level of tidal heating that's going on in them. We don't know much about them at all, actually. And so again, I'd like to point out to you that there are great things to still be discovered in the solar system. So here's another picture of the Uranian system. And one of the things that's interesting about this is that this system is actually on its side, whereas most planetary systems, their moons and their rings are pretty much in the same plane as their orbital plane. This system is on its side. It's a busy system. It's a system, like I said, that really merits more studies. And you can see that there are a lot of small moons. Some of them been discovered by the Hubble Space Telescope since we've been able to tune it to monitoring Uranus. Um, and there's definitely multiple rings that were discovered. So anyhow, this is an interesting system. It probably has possible sites. Um, one of the moons that I'm going to call out is Miranda. You can see it in the image on the right. It's in the very outer orbit. You can see it at sort of the 8 o'clock position along its orbit. And it's kind of an interesting moon that's sort of got an old surface that seems to be untouched for billions of years, and then this other side, which is a complete mess of scarps and cliffs at odd angles that are global to about half of the body, and people really don't understand what this kind of facelift was due to, but some people are arguing that it might have been a collision, but it's an interesting moon and it's right, and so I thought I would give it a shout out. Moving further out into the solar system, we have the Neptunian system, and one of the moons we're going to give a shout out to here is the moon Triton, and Triton is actually a captured moon, captured from something called the Kuiper Belt. Now, I think you all are aware of or heard of the asteroid belt, which is a belt of chunky material that exists between Mars and Jupiter's orbits. Um, so it turns out that somewhat recently, in the last 20 years, we discovered that, in fact, there seems to be another quote unquote asteroid belt that is out beyond the orbit of Neptune. And Pluto is actually in this asteroid belt, and um, this is one of the reasons that Pluto was demoted from a planet to a dwarf planet, is because it actually is a large Kuiper Belt object, if you will. So it turns out the Kuiper Belt's full of many dwarf planets, and at any rate, we could either continue to add planet after planet after planet to our textbooks, or we could say, look, these are objects that belong in this belt. They're a family of objects that are remnants of the formation of the solar system, and that's what happened to Pluto. So if you think about it, let's look at the size of Triton there in the lower left and compare it to the size of Pluto, and you can see that Triton actually is bigger than Pluto. So if Triton hadn't been captured by Neptune and called a moon of Neptune, um, we don't know what its orbit was, but maybe it would have been discovered before Pluto was, and Triton would have been named Pluto by Clyde Tombaugh back in the 1930s. Of course, we'll never know that history, but I want to talk a little bit about the Kuiper Belt, and I want to talk a little bit about Triton and a little bit about Pluto. And show you about this very rich Kuiper Belt that, again, has only been known for about 15 to 20 years. So we'll talk about that. Now, one of the things that for why we know that Triton is a captured moon is because its orbit is backwards. It's in a retrograde orbit. So I want you to look at the image of the moon orbits around Neptune on the right-hand side, and you'll see the arrows. The arrows are the directions of the orbits. And it turns out that all those moons and the inner moons there are all moving in what's called a prograde direction. They all move in the same direction around Neptune that Neptune is rotating on its axis. So they call it prograde, going in the same direction as the planet rotates. Now, if you look at the outer moon, that's Triton, it's going the opposite direction. It also is in a highly elliptical orbit, and it is also very far from Neptune. And you put all of those things together, you can see that it did not co-evolve with the Neptunian system and form out of the debris that Neptune formed from. Okay, so here is my brief slide on the Kuiper Belt and a small inset here showing various dwarf planets that have been discovered in the Kuiper Belt. You can see Pluto with its moons, and of course its largest moon, Charon or Charon. It's pronounced so many different ways by different people. I'm going to call it Charon. Um, and so you could see these other dwarf planets. In fact, you can see that some of them have their own moons. In the case of Haumea, it has 2 moons. Pluto actually has 5 moons. Okay. If you look at the uh, lower left diagram, then you can see the planetary orbits. You see Jupiter and Saturn, and then Uranus, and then Neptune. And Neptune is the deep blue one that's sort of at the 8 o'clock position on the diagram. Um, and so what you notice there is that the Kuiper Belt reaches this broad band of small bodies and asteroids and small dwarf planets reaches all the way into the orbit of Neptune. And so it's not surprising when you think about it that Neptune actually captured one of the larger bodies of of the Kuiper Belt, and we now call that moon Triton. You can see Pluto's orbit is highly tilted and is highly elliptical. It actually, at its farthest point, is much farther from the sun than Neptune, but at its closest point is closer than Neptune. So that's another indication that Pluto is really not the same kind of beast as the other main planets. Okay. Um, Now, if you want to see what the orbits of some of these Kuiper Belt objects are like, you could see that some of them are highly elliptical, like Pluto is, and also um, are tilted relative to the axis of the solar system, or the plane of the solar system, which goes by the name of the plane of the ecliptic. So Eris is the big moon up at the top there. If you look at the diagram at the top right, it's across the top. Eris is large. You can see it as the green orbit in the lower right hand diagram of orbits. And you can see Pluto as the magenta, and then we have Makemake, as you can see in the upper diagram. It's a little bit smaller than Pluto. It's also got an orbit here that is comparable to Pluto's. It's pretty interesting. So as you can see, this is just a small smattering of the objects that are known. It turns out that we continually are learning more about them. And in fact, believe it or not, we now have a spacecraft which is flying through the Kuiper Belt. It's called the New Horizons, and it flew past Pluto just a few years ago. So we'll talk about that very briefly. I want to say that I believe I have a small video on the Kuiper Belt, and I think this video is video 8, the undiscovered country, how many more Plutos are out there. And so it's a little bit of a discussion of what we expect to find as we move out through the Kuiper Belt with the New Horizons spacecraft. That video is about 4 minutes long or so. There's another video that's linked at the top of this page that if you want to cut and paste it, you can, and watch that. It's a little bit different. It's about the theory of Kuiper belts and how we've discovered Kuiper belts around other planets. Around other stars. We've actually been able to measure their Kuiper belts and see the influence of large Neptune-like planets on them. And then it's a discussion of some of the theory behind that. It's very quick, and it's really quite cool, actually. But I've decided to show the other video on Canvas. So the last moon that we're going to look at in detail here is Neptune. And this is the only slide I have on Neptune. And so one might look at Neptune and think that it looks a little bit like a cantaloupe. You can see in the upper right image the lower part is very cantaloupe-like, but the other part has this very, very rough terrain. And so, again, we see a body which is geologically very interesting and very active. And you might notice in the upper part where the rough terrain is that there are these black spots here and there. And well, it turns out that these black spots are left over from methane plumes or geysers. And this is one of the first objects to be discovered to have these things. Now, again, the only images you're seeing here are from a Voyager flyby. It's a one-shot deal. It happened back in the late 80s. And so, again, there's a whole world here to discover if we could have a spacecraft orbiting around Neptune. Again, I'm going to remind you this is a captured Kuiper Belt object. It is actually a little larger than Pluto and is in a retrograde orbit going backwards around its planets with respect to the other moons. It's the only internal energy that we could think that this body had would be due to radioactive decay. There's no real tidal heating that could be happening with this planet. It's too far away from Neptune. I didn't mention on Enceladus that it's possible that radioactive decay is part of the energy source which powers that. Anyway, you have these methane geysers. You can see them here in the bottom picture, and the photograph-looking one is not real. It's an artist's rendition, and the idea is that there's probably some surface layer below which which is very cold, and then there's this sort of very cold methane that in a sense serves as an antifreeze mixed with water, and you get these methane / water geysers. Okay. And then I just want to remind you that it's very cold, minus 230 degrees. Now, if there was any possibility of life on this moon, it would probably be much deeper in the interior. We're not certain. And again, there are so many possibilities about what's out there in the solar system. We should not look at these as dead worlds. I know they seem to look dead, but they actually are very active in many ways, and who knows what's in them. And we should have an open mind and go and study each one. And I look forward to the day when we know as much about all of these bodies as we do about all the different various continents on the Earth. So this brings us to our final slide for the lecture. It is basically a comparison of many of the objects in the solar system that are small and rocky, if you will. Of course, we have Earth and Venus and Mars, and then we have the Ganymede from Jupiter and Titan from Saturn, then the planet Mercury, then Callisto from Jupiter, and Io from Jupiter, and then our own moon, and then Europa from Jupiter, and Triton around Neptune, and then Pluto. So those last two being sort of Kuiper Belt dwarf planets, one being a captured moon. So some other Kuiper Belt objects are shown just for fun here. Pluto in the center highlighted. People got a little cutesy. Next to it is Santa. The one next to that is the Easter Bunny. And I think those are names that were given before the International Astronomical Union gave them official names. And so then we have Eris, which again is bigger than Pluto, which is a Kuiper Belt object, and Sedna, another large one. And at the very bottom, below the yellow line, are the moons that go with each of these Kuiper Belt objects. So below Pluto, you see 3 of its moons. It actually has 5, Charon being the largest. And then you have Santa has 2 moons, and then you see that Eris has 1 moon. So it's not uncommon for these bodies to have captured other objects, probably didn't co-form with them. and we would find that they're made out of a completely different composition of elements and whatnot. So it'll be very interesting to study them. And we have a whole world of solar system. It's very exciting to go out and explore. Okay, I hope you've enjoyed this lecture, and I hope that you've learned something about how much is really out there and how the moons of these gas giants can be very interesting. I want to say that you definitely need to watch the videos. I know there's quite a few of them this time, but they're all very short, and they augment the lecture very, very well, I think, and put some good visuals and some extra information on them. Don't forget to take the attendance quiz, A-C9, and then, of course, the quiz from the lecture and is Q-C9, and then, of course, then there's the homework, HW-C9. All of those due April 17th at midnight. And so if you have any questions, again, there is the discussion board, which so far has received no attention. And I've been opening a Zoom channel at noon on Tuesdays and Thursdays, for which I've had no attendance yet. But I'm there for you if you need me. I've tried to be responsive when you send me Canvas messages. And so I hope you all are staying healthy, doing well, and social distancing. And even though there's talk of, going back to normal, I want you to understand that until there's a vaccine, we will have a new normal. We'll probably still be social distancing. We just might not be completely quarantining ourselves from each other, but we'll have to practice social distancing behavior and probably wear masks until we actually get the virus under control. So I just want to say, don't let down your guard, and it's going to take a while to get back to normal. Anyhow, I hope you enjoyed the lecture, and we'll see you next time when we talk about habitable zones. We're going to head out to talk about liquid water on the surface of other planets and talk about all kinds of different stars that are out there, and eventually, soon after, talk about all of the other planetary systems that are out there. So we're heading out of the solar system, folks, and it should be, I think, fantastic and interesting, and you're going to really get your astronomy's money worth now as we head out. So take care, and good luck on the quizzes and the homework.